N. Okay, so here this potential becomes larger than this potential. When it becomes like that, its voltage exceeds this potential, this becomes collector base junction also as forward bias. So at that particular input, the switch will be on state. When I have bias such that the level of my input pulse is coming something like that, narrow width pulse. Level, when it appears here, it is such that it makes this one forward bias and this also has forward bias. Not for this VCC, because it has to come in the your below that forward bias conditions also. But anyway, when it becomes saturation, this voltage drops tremendously and this becomes larger than that. So this becomes larger than that. This is also forward bias, this is also forward bias. So for this magnitude of the pulse, I design this bias. When it appears, both of them become forward bias. It is positive here, this is my 0, this is my V. So that will bring it to the on state. Okay, when this pulse is not there, that means this is as it is, whatever bias is there, it is as it is. At that bias, I make slightly negative. If this bias I make slightly negative or less than V gamma, you can say like that. Even less than V gamma, it will become reverse biased. And at that time, this is also reversed bias. So when we bias it at that time, such that collector base junction is reverse bias and emitter base junction is also reverse biased. At that time, no current will flow through this because both the diodes are reverse bias. Reverse bias resistance will be very high and no current will flow through this. Negligible current will flow. So this one will call as off state. So this pulse applied takes it to on state, takes it to off state. This pulse will be coming from my circuit now. Now it will coming from my circuit, which will control the switch, take the switch into on state or off state. The circuit is generating this control voltage V that is operating this inverting amplifier. Now it is biased like that. So what is the initial bias? Initial bias convenient to us will be initial bias. When pulse is not applied, that is the initial bias. Switch should be off state. So switch is biased such that it remains in the off state, not in the active state, active region. Okay, so off state is your nothing but I also call it cutoff region. Cutoff region. And the bias is such that this amplitude which is coming from my circuit, when that applies, it will go to this one on state. On state we also call as saturation region. Saturation region. Okay, so saturation region and cutoff region. So I have initially bias in the cutoff region. What should be that bias? It should be designed according to the pulse that is coming as the input. It goes to saturation region. So what are the voltages when it is cut off and when it is in saturation? because this will be needed in designing of the multi-vibrator. You already know that, but I have to repeat that because the subject says this material to be discussed. So I have to do that as a repetition for some of you. But anyway, it should be useful to majority, and that's what I'm thinking. So what if the switch is off? That initially I find switch is off. So this was my transistor. It can be transistor, it can be op amp, it can be anything. This was off. Here we have applied VCC. So whatever is RC, R1, R2, this I can ground for the time being. Put a resistance, your complexity will grow for the understanding or something like that. So we can add the resistance here with the cell bias and it will be there in the circuit for off state, on state, that control. So if it is off state, what is this output? Okay, this output will be VCC minus VCB, collector base reverse bias voltage. Okay, when the emitter lead is open circuit. VCC, sorry, it should be ICBO. It should be ICBO. But anyway, that collector base junction, when this is open circuit, it is related to your ICBO, that way I can say. So when this emitter lead is open circuit, that voltage generated across these terminals, that is your reverse saturation current, into some resistance here, that is called a VCBO. VCC minus this VCBO. Oh, no. I'm talking off state, as you are right. Off means no current is flowing through that, only the reverse saturation current is flowing. Okay, so VCC minus VCBO becomes my output voltage, V0. And this voltage very small, you can consider like that. What is that? ICBO, that current will be passing through the internal resistance, reverse bias resistance, and this one. So reverse bias resistance dominates there. So that way you can say this voltage in the reverse bias situation is very small. So that will be my V0. So it will be approximately equal to VCC. When it is this one, what is IB at that time? Current IB that will be flowing in the off state. Okay, so this IB will be, I'm calling it IB as off state. Okay, IB cutoff. Will be this IC. What is this IC? IC cutoff. Divided by HFE. There are two kinds of HFE, HFE maximum and HFE minimum. If only one is given, so IC cutoff by HFE I can write like that. Okay. Normally in cutoff, we take HFE maximum to compute my IB cutoff. When it is for saturation, I take IC saturation divided by HFE minimum. So that way it will be computed. So this IB cutoff is coming like that, and that's what I have biased this. Using that, we can calculate other values. What will be my VV, this voltage? I can compute by that. This is my IB. Some current will be flowing through this. This is my VCC, some current is going here, some current is going through this. And Thevenin's equivalent circuit, you will be able to solve it. What is the value of your IB? I'm not doing that. I'm leaving it as a homework for you. You can do it and put your questions to me. How to solve that IB when this is my R1, this is my R2. I'll find the current through this R1 first. Total current through R1. Then I'll find the current flowing through this R2. Okay. That current should be equal to this current minus this IB. IB I have computed according to the cutoff IC and HFE in that way. So you will be able to find what is VB at that time, at which it is already biased in the transistor. So HFE will be read from the manufacturer data. IC cutoff is also manufacturer data. We are not putting anything as a design parameter there. When it becomes your on state, then what happens here? This is my base. This is, I'm taking NPN because I want to talk about the positive logic. So this is my ground. This is my VCC. This is my RC. Same thing I'm taking here because design is not changed from one state to another. So if that is there, what is my this output? V output will be VCE saturation. Okay, between this and the ground, that's VCES is coming like that. VCES is once again manufacturer data. By design, I cannot change the VCES. I can change in the active region, load line, operating point, and all that I can change, but VCES, this I cannot change. That is the manufacturer's data. So V0 will be VCES. What is my current IC? IC is coming directly through that. That will be your ICS. So you have to find RC such that VCC minus VCES divided by RC should be larger than or equal to ICS. If this current is larger than ICS, even equal to ICS, it will be driven in the saturation. So that is the design parameter I'm choosing from this for this RC. What will be my IB once I have got this ICE? IC I have got. What is my IB? IB will be IC, this IC, ICS greater than ICS divided by HFE minimum. So if my base current is greater than that, I can call it IBS. IBS is nothing but, okay, VBES divided by the internal resistance of the base emitter region. I call it base 2, the actual base, that is spread resistance, or B prime. So VCS by this becomes my IBS. Okay, so it should be VBES, that will be smaller than your V gamma because I am going in the saturation. That is given in the manufacturer data as V sigma, saturation voltage. Okay, so that is given to us. You find like that. What is that? How to control this IBS when the voltage is applied here? Here it becomes VB plus the pulse amplitude, V of the pulse. At this point, this is the pulse applied. When that pulse is applied, this is my VCC. How much current will be flowing through this R1? There are two supplies now. VCC and VB, that is actually comes as design plus VP there. By changing these two, I can find the value of R1 and R2 such that my IB becomes IBS when this VP is applied, and then the circuit will work for the on state. So on state to off state, I'll be going manufacturer data is VCES, manufacturer data is VBES. VCES is given, VBES normally written as V sigma, not V gamma. V gamma is a cut-in voltage. VC is your VBS also written as V gamma, VCS like that. That is manufacturer data. Taking that into consideration, we have designed RC, R1 and R2. Such that initially it remains in cutoff. When this VP comes, it should go in the saturation region. Is the problem clear? What we want to design now? In the circuit, I will be putting this now. I think there is no question. You already know this. I have just revised your subject that you have learned in your first year. Can you hear me, Professor Sengupta? Am I audible to all or not?
Yes, sir. You're audible.
Okay, it's fine now. Then I said that this is the switch that I have got. I want to control that. For that, I have designed a bistable logic. When the pulse appears, first pulse appears, that will change the state from off to on. When the second pulse appears, that will change it from on to off. And you can say time difference between the two pulses, I will control by some other circuit that will be given as input to this thing. Okay, so this is the one I'm controlling, and here is the control voltage that is coming to me. So when I say bistable, I'll be using two NOT gates. I use as a NOT gate there as a symbolic form. Remember, it is like that. Ground. This is another NOT gate. I'll be coming for cell biasing also, emitter resistance later on, but let me understand that first. Okay, so what we had decided in the previous study lecture, that this and this are joined together. Okay, so two NOT gates are joined together. They are not joined directly. They are joined through resistance here. Okay, and what is the biasing of this transistor? It is a resistance coming like this. Here, the resistance comes like this, and this is connected to the base. You see, this is the output connected to the base of this thing. This is my VCC. And I have to bias this. This is the resistance. Biasing we do with the, you can say, symmetrical resistive networks. Okay? And it will change the state according to that. Here it is something like that. Here it has come. I think it is coming here. Directly it is joined here, sorry. And from here it is coming like this. It is coming here. It is joined here, okay? Nothing like that. When this base is to be connected, this one will be connected by similar resistance. The way it is coming there, I am coming like this. Connected like this. So this output is connected to the input of this inverter circuit. This is connected to this inverter circuit, and I have biased it, both the transistor, to remain in off or on in two states. For both inverting amplifiers. Active region is not there. So it is not remaining in the active region. So either on or off, it is going. So now what is this? Let me put the value, because this is my RC. This also I am putting as RC. I can put it RC1 and RC2 also, but that is of no gain. Why should I go for it? I am calling it as R1 here. In a symmetric resistive network, I can put this also as my R1. I can put this as my R2. This also I am putting my R2. And now this I am putting as my RB. Remember, RB, by which the output is connected to the input of the other one through the resistance RB. Similarly, this also becomes my RB. Okay, so these two resistances that couple the collector to the base of the next stage, this is RB. Now, nothing to do. I have not done any other biasing. I have ensured that by R1 and R2, transistors will remain in either off state or on state. In between, nothing is there. So both of them are designed identically. So identical resistances are there, identical voltage are applied to that. Is that okay? Now, suppose by some electrical, I have switched on the circuit now, it will not work until unless some noise, electrical noise appears. So remember, if the world becomes noiseless, entire electrical, your equipments and computer equipments, electrical science equipments will fail. Noise is essential for our survival. That is our bread and butter. So noise, we cannot get rid of that. Somehow the noise has to come. The room is ideal, no circuit will work. So I have switched on the circuit. After that, some noise has come, some sparking has come, maybe some thermal noise has come, maybe something that is converted to electrical form, and it has changed this current, let us say. This is changed by delta IC. Increase, let us say, delta IC increases. Noise has made this design current that I have done for both of them. I don't know which one is going in which direction. Until noise comes, they are remaining stable at that particular, because both are identical, so nothing is working on that. So this has increased by delta IC. When it has increased, this voltage decreases. When delta IC increase, in transistor Q1, I'm calling it as my Q1 or T1, whatever name you give, I'm calling it as my Q1 as this transistor, I'm calling it Q2 as this transistor. Okay, so delta IC increases in Q1. It will make what? VC1 decreases. Voltage drop across RC will increase, so at this collector voltage VC1 I find a decrease. Okay, so this is also VB2 Q2 decreases because VC1 is coupled to the base of the second stage, so that also decreases. Okay, so VC2 decreases. Sorry, VC2, VB2 decreases. In that case, VC2 increases. Why? Because IC2 is reduced. When VB2 is decreased, IC2 will be decreased. IC2 decreases. IC2 decreases, so VC2 increases, less current is flowing, so drop across RC is less, RC in the Q2 transistor is less, so the voltage is increasing. As a result, this VB2 increases, that VB1, as a result, VB1 increases. Okay, this will continue. VB1 increases, at that time what will happen? VB1 is increasing, then more current will flow through this RC of the Q1, so VC1 decreases. More. And VC1 decreases, again the same cycle follows. So ultimately what happens? VC1 has decreased to very low value. So Q1 becomes off. Q1 becomes off because our biasing is like that. There it will reach a stable state. So Q1 will become off and Q2 becomes on. If the change in current has taken place in Q2, the other way it will happen. Q2 will become off and Q1 will become on. So when I switch on the circuit, this, I call it bistable multi-vibrator, I give the name because two stables are there. It will be latched to one transistor as on state, one as off state. Suppose I am taking my output at this point at Q2, V0. So at this time I can say V0 is leading for the control of the switch, and switch will go to an on state. V0 will lead to on state. Okay, if the change has taken some other way, then V0 will be leading to off state of the switch. That will be stable state. And when the pulse is applied to which one? The one which is on state, I will apply a negative pulse there. It's not that which is off state, I am applying a positive pulse. That is also possible. Which is off state, I can apply a positive pulse there, or not at the same time, or I can apply a negative pulse to the particular transistor component base which is in the on state. So both way I'm talking about the positive logic. Yesterday I described the positive logic. So I give a pulse here. At that time Q2 will become off and V0 will become high. Q1 will go to a saturation. Pulse becomes high, large current will flow. This becomes your VCES. This becomes your almost equal to VCC because no current will be flowing through that. both are reverse bias in this case. So that is the way. Question here, it's okay. Okay, so this is your bistable multi-vibrator. I call it bistable multi-vibrator. So from a narrow width pulse, I can control on and off state of a switch, and both will be stable. So my pulse need not be having that much width during which the switch has to be on. No, I can control the frequency of my this pulse train or impulse train that will make the switch on and off according to that. When the pulse is appearing, it is making it on and off. So we call it bistable multi-vibrator to make a switch on and off state. Okay, I will explain other vibrators at the same time in the same circuit. Let me see what is happening. Design I will take up separately in the next class. Yeah, it's like that. What is your astable, quasi-stable state? It is same thing. This is my Q1. I think I explained yesterday using the two NOT gates. Okay, so NOT gates become on and off according to that. I'm taking the same thing with the help of this transistor biasing. It is this. Okay, this one would be biased by these circuits, this resistance. This is my R1. This is my R2. There is another transistor, second transistor. A conceptual circuit, when I start talking about the design, these concepts will help you in easily understanding the things. It becomes like that. Okay, this is my VCC. Connection I am going to make. What way? I am taking from here this resistance. I have taken from here. I connect it here. Okay. This resistance I am saying as my RB. This is my RC. Remember, I am saying RB, not base resistance, but it is resistance coupling the collector of one stage to the base of the second stage. Okay, similarly from here, there will be one resistance RB. It will be going like that. Connected here. So this is RB, this is RB. It was bistable. When I want to make it monostable, this was my R1, remember? Okay, R1. This RB will not be there. I'll be putting one RC here, capacitor here. In one of the arm, I'll put a capacitor. In other arm, this RB is remaining, so it becomes my CV. So this is a capacitor, this is a resistance, and the multi-vibrator becomes like that. Here, our assumption will be that this is your off state. Okay, and this is your on state. That means voltage across the capacitor is nil, 0. This voltage is 0. It is on state, so it is 0. So voltage initially voltage across the capacitor will be 0. So this is off, this is your on state. Okay. Now what happens? I apply a trigger here. Nothing like any AND gate, that circuitry for changing the position of the trigger. Trigger is coming to this point only. This was my off. Okay. When this is applied, this becomes on. Okay. This becomes on. So this voltage becomes less. That is your VCES. This voltage becomes VCES. This voltage reduces. So this will become on. This becomes, sorry, off. Less voltage coming, so this becomes off. It was on, now it has become off. It will take some delay while coming from here to here. I'll talk of that delay later on. So it has become off state now. When it has become off state, VCC minus VCES appears here. VCC minus VCES appears here, and the same thing appears at the base, because initially capacitor is having zero charge, the chargeless at that time. So it comes here. So this difference, what the difference? Difference was your VCC minus VCES. That is the difference. VCES earlier was there, now it has become VCC approximately equal to this. This is the difference. That difference has come at this point. Okay, so at this point, this is the difference coming. This becomes very high. Now the pulse is gone. This pulse, this voltage has appeared. This pulse is gone. This is removed. So it is this. When that has come, it will be driven into off state. Sorry, on state. Sorry. It will driven further into on state. Even if this is gone, it will remain in the on state. VCC minus VCES has come here. So it remains in the on state. And now the capacitor starts charging. Through what? This RC, CB coming to this point. Okay? So capacitor starts charging RC, CB and this point. It will start charging. When it starts charging, this voltage starts decreasing. Okay? When the capacitor is charging, this voltage will start decreasing, and when the capacitor is fully charged with this voltage, cutoff voltage, then this will become very small voltage. That will be your VBE. It will become VBES. It will become so small that it is your VBES. So this will take the collector voltage to be VCES. Sorry, VB is decreasing. Sorry. So this will be equal to your cutoff voltage. It will be less than V gamma. So this voltage will be less than V gamma. So it will become your cutoff. Okay, it becomes your cutoff. Then this voltage becomes high. So what happened? When this pulse is applied, a high voltage appeared at the V naught. This is my output. Cutoff voltage remained high. After that, it starts decreasing. It comes out to this point, depending on the time constant, like this. So this CB, RC coming, discharging through these resistances. Okay, this was your R1 and R2, like that. It is discharging with this. Okay, so it has come like that. When the next pulse comes here, again it goes like that. It falls like this. How to make it flat? That will be talking in the design parameter. It goes like that, it comes like this. So if your time constant is reduced, it go time constant becomes high, rather becomes high, it has gone, and then it reduces, it becomes constant, almost constant here like that. It falls after that. Anyway, I'll come to this finding CB, and this one. CB controls this width also. So I'll talk about that in the next class. This we call it monostable. Monostable circuit, multi-vibrator. Multi-vibrator, monostable diode is coming like that. So capacitor will be charging and it will be dropping the voltage at the V output to some voltage here. If voltage dropping here, there's voltage dropping here also. If voltage dropping here, the other way around, V naught I'm taking here, isn't it? Earlier it was on state. What did I consider? It was on state earlier. So when this voltage is getting confused, it was off state initially. Oh, I made a mistake. Initially this should be off. Okay. Initially this is off and this is your on. No, right, wrong. This should be on initially and this should be off. Initially it should be off. I think I will explain later tomorrow. It should be on and this should be off, and here is the negative voltage applied. If there is negative voltage applied, I can apply here, a positive voltage here also I can apply. This voltage will increase and it will go to the cutoff that way. I think that is the thing. Negative voltage here, sorry, negative voltage here, negative pulse here. Sorry, I made a mistake. Negative pulse here, or you can say I will be applying a positive pulse here. So this was your on, this was your off initially. Now applying a pulse either here in positive or here in the negative, this becomes your off now. When this becomes off, this high voltage comes here. Okay, this will make this one on. So off will switch to on, and that's what the things will be happening. I think the capacitor charging I was not able to explain, that's why. Anyway, I'll do it tomorrow again. Tomorrow in the sense Monday I'll do in a better way with clear and better diagram that way. So I think today's time almost approached. If there is a question, I appreciate. Students are not many, but anyway, multi-vibrator fully consists of your module number 3. So that's why we have to put around 4 to 5, at least 5 lectures, 5 to 7 lectures on this one, multi-vibrator, before we come for the quiz 3 exam. Quiz 3 will be on 3rd March. I have already announced, I am announcing today also. 3rd March will be your quiz 3. And at that time, I don't think any kind of holiday etc. is coming. So our classes we are not losing. So March 3 we finish that. Any question here? Students are less than 1/4 right now today. So anyway, I have to go by that. I cannot change the subject and syllabus. So I have to teach that only. I'll be talking of design at that time. Some numericals will come. Okay? Okay, Professor Sen Gupta. So we take leave now. No
Yes,
question
sir.
then.
Okay,
Thank you.
sir.
Good day.
Thank you.